In this video, we're going to look at the formal definition of the limit of a function in real analysis, and this is something called the Epsilon-Delta definition. So if you're following along in the playlist on real analysis, thus far we have looked at the epsilon definition for the limit of a sequence of real numbers. We also looked at a separate definition that allows us to talk about sequences that tend to plus infinity or tend to negative infinity, having a limit of plus infinity or negative infinity respectively also. What we're now going to do is expand our repertoire of things that we can take the limit of further to include functions. And you'll see the higher you go in analysis, the repertoire of things that you're able to take the limit of is going to get bigger and bigger and bigger. The entire subject is all about limits. It's all about convergence. And whilst the things that we're going to talk about limits of get more and more complicated, the actual fundamental idea of what convergence, what a limit means remains the same. And that is that whatever you're taking the limit of must get and stay indefinitely close to this thing that you're calling the limit, the thing that you're saying it converges to. That is the central idea of all of analysis. And all that changes is the technicalities of how you get and stay indefinitely close to. Those things change, you know, what indefinitely close to means, or what close to means, and what it means to get and stay, the technicalities of that can also change. But the overall intuition, the idea that these things, whatever it is that you're taking the limit of, must get and stay indefinitely close to this thing that it's converging on, this thing that we're calling the limit, that is crucial to all of analysis, and it remains the same. So let's begin with the intuition behind what the limit of a function means. So we're going to be looking at simple functions, which are real valued functions of a single real variable, and throughout the video we will call our function f. So f is going to map every real number onto another real number. And one of the incredible things about real valued functions of a single real variable that makes them easy to understand is that they have a graphical representation, and this is of course something we're all taught in school. We can think about putting the domain real line in one dimension, and we usually put it in the horizontal dimension like so, and then putting the codomain real line in another dimension, orthogonal to the first one, and we usually put it in the vertical dimension like so. Then, to graphically represent the function, what you do is you go to each point in the domain, and we've got an example point A here, and for each point you ask where is it being mapped onto. So for A it's being mapped onto this value here, f of A, and you go up or down as much as is necessary so that you are in line with that level in the codomain dimension, and then you plot a point there for what this point in the domain is being mapped onto in the codomain, and you do that for every point in the domain, and then you will have a graphical representation of your entire function. So 12-year-olds understand this. Let's move on to limits. So to get some intuition for the limit of a function, we're going to take an example, and the example that I'm going to take is going to be given by this function rule here. Now, this is an extremely simple function for all real numbers that are not equal to my point A here, because for all the other ones, this bit here is going to cancel with this bit here, so we'll just be left with this. So for all the real numbers apart from x is equal to a, it's just going to map them onto themselves. However, at a, that's not the case. When you put a into this function rule, it breaks because you're trying to divide by 0. You're trying to have the multiplicative inverse of 0, which is undefined. So actually, at x is equal to a, this function is undefined. So graphically representing this, we have our beautiful f of x is equal to x, and then we have a hole at x is equal to a. So this is where the idea for the limit of a function comes from. So at x is equal to a, we cannot ask what the value of the function is equal to. It's undefined. However, we can ask a different question. We can ask what's the limit of the function as x approaches a. And what this means is what does the value of the function converge on as x approaches a. So for all these points around x is equal to a, the function is defined, and we can look at points closer and closer to a in the domain, and we can look at what they're being mapped onto in the codomain, and we can ask, are the is the value of the function converging on anything? Is it getting closer and closer to something as the points in the domain get closer and closer to A? And the answer in the case of this example is clearly yes. The value of the function converges on A as x approaches A. So the limit as x approaches A of f of x is equal to A. So it's where you would have expected the function to map A onto if it was defined there, where the hole is in the graph. Thinking about this a little bit more deeply, the reason we can say that the function converges on A as x approaches A is because it is true that the function is going to get and stay indefinitely close to A as x approaches A. So what you can think about doing, and indeed we'll formalize this in a moment, is we can think about putting a little epsilon interval around A, and of course we can make epsilon indefinitely small. That's going to form part of our definition, this epsilon-delta definition. And we will be able to then find points, and I've drawn this on here, a point that is potentially very close to A in the domain, but this point, we will be able to find a point such that when you look at what it's being mapped onto, it will be that epsilon closeness, within that epsilon closeness of A, it will be within this epsilon interval. So if you go close enough to A in the domain, you will be within your closeness, your epsilon closeness of A in the codomain. So the value of the function then is getting indefinitely close to A as you get closer to A in the domain. And not only does it get indefinitely close to you, but it also stays indefinitely close to you, because if we think about this point, it's being mapped into that epsilon interval, and then clearly also all of the points to the right of it, between it and A itself, which is here, all of those points are going to be mapped into that epsilon interval as well. So not only does the value of the function get within that epsilon interval, but it stays within that epsilon interval for all of those points from that boundary to A. So let's turn this intuition into a formal definition then, and this is the epsilon-delta definition that the entire video is about. So the meaning of the limit as x approaches A of a function of x equaling some value which we'll now call L, and note in our example the value of L was equal to A, it was equal to the same thing as you were approaching in the domain. Now in general, of course, that's not going to be true. That was just true because of how simple this example was. So in general, we need a different symbol for the limit, and we're denoting that L. And the meaning of this, it's defined to mean this. And don't worry, we're going to draw a picture and understand what this means, but firstly I'm just going to read it to you. So it says, for all epsilon greater than 0, so epsilon's a real number, there must exist another real number that is greater than 0, which we're calling delta, such that if you look at any point in the domain that is within the delta interval around your point A that you're approaching, so look at a delta interval around A, so from A minus delta to A plus delta, all of those points inside that interval, they must be mapped into the epsilon interval around the limit L, so the interval L minus epsilon to L plus epsilon, apart from your one point that is excluded, which is the center point of the interval itself, which is the point A. So we have to cut that out of the interval, because of course the function might not even be defined at x is equal to A, or for instance I could have defined this function so that at A it was something completely different, right? It could have been down here. Let's understand this with a picture. So I've drawn a picture here. So this is now the graphical representation of our function f of x. Here is our point that we're approaching in the domain, x is equal to A. Here is what the value of the limit of the function as x approaches A is clearly going to be. You can see that as you get closer and closer to A in the domain, the point that you're converging onto, the value you're converging onto in the codomain is going to be that whole value there, which is L here. And I've said that actually the value of the function is something completely different. It's down here. So the actual point for x is equal to A, where it's being mapped onto, is down here. So let's now use this picture to understand why this definition captures the intuitive notion of convergence. So it is saying for all epsilon greater than 0, and that's really saying however close you want, however indefinitely close you want to be to the limit L, construct the epsilon interval around L, and that's what I've shown here in blue. So here's the lower bound of that epsilon interval, and here's the upper bound of that epsilon interval, and note that these are open intervals, so L minus epsilon to L plus epsilon. So for however indefinitely close that interval is going to be, however indefinitely small it's going to be for all epsilon, there must exist another interval, a delta interval, around the point in the domain, around this point x is equal to a, and that's shown here in red, so a minus delta to a plus delta, again an open interval, and here is the lower bound of that interval, here is the upper bound of that interval, such that for all of the points inside that delta interval, they are going to be mapped into, by the function, the epsilon interval around L. So what that is saying is however close you want to be to the limit L, you must be able to find an interval around your point x is equal to a. And yes, you might have to make the delta absolutely tiny, such that all of those points are mapped into that closeness around L, i.e. all of their function values are that close to the limit L. And that is capturing the fact that they get indefinitely close to L because of the fact that this must be true for all epsilon, no matter how small it is. So for indefinite smallnesses, it holds true, and also stays that close to the limit L, because it's not just the endpoints, for instance, of the intervals that are being mapped into there, it's all of the points inside that open interval that are being mapped onto there. So all of these points are being mapped that close to the limit L. So it's the value of the function is truly staying that close. Now note, there is one point inside the delta intervals around A that is excluded from this criterion of being mapped into the epsilon interval, and that is the point A itself, the centerpiece for the intervals, as we saw here in this definition. And that is because the value of the function at A isn't actually important at all when we're considering what does the function converge on as x approaches A. And this picture makes that quite clear. The function converges on this value L here, the limit, but the value of the function is something totally different, and clearly this is not going to be inside this epsilon interval. So any epsilon interval that's got a boundary smaller than being over here, this difference between L and f of a, is not going to include f of a, so no delta interval is ever going to be able to map entirely into that epsilon interval if we were including the point x is equal to a, but we're not in this definition, and that's crucial that that's not included. So to summarize the epsilon-delta definition, the meaning of L being the limit of the function as x approaches a is that for all epsilon greater than 0, there must exist a delta greater than 0, such that if you consider that interval, the delta interval around a minus delta to a plus delta, all of those points inside that delta interval, except for the centerpiece itself, a, must be mapped into the epsilon interval around L. And you must be able to find a delta interval for which that is true, that they're all mapped into the epsilon interval around L for all epsilon. And that is capturing that idea that the value of the function gets and stays indefinitely close to this value L, which we are calling the limit of the function, as x gets closer to a, as x approaches a in the domain. Now you might think that would have been a nice place to end the video, however we're not going to, because we've still got a lot of interesting stuff to look at regarding this definition. So we're now going to look at something that is an equivalent formulation of this concept of the limit of a function. So we'll see how it's equivalent to this epsilon-delta definition, and it's called the sequence characterization of the limit of a function. So let's firstly look at how this implies the sequence characterization, and then we'll look at how the sequence characterization would imply this, meaning that they are equivalent to one another mathematically. So my first claim then is that if you take a sequence in the domain that converges to the point A, so its limit is A, so that's this sequence in green written out here, x1, x2, x3, a sequence of real numbers, and they're all in the domain, so they're drawn on the picture here, and they're converging to A. Now importantly, none of the terms of the sequence are allowed to be A, because remember, we don't actually care what the function is doing at A. So my claim is if you take such a sequence, then if you look at its image sequence, meaning take each one of these terms in the sequence and look at what it's being mapped onto by the function, and then create that corresponding sequence. So here's x1, here's its image, here's x2, here's its image. So this is what I'll call the image sequence. My claim is that that image sequence will then converge to something in the codomain, and it will converge to the limit of the function if the function has limit L as x approaches a. So I've written that simply like this up here. If we have a sequence xn that converges to a, where the terms of the sequence are not allowed to equal a itself, then the image sequence f of xn will converge to the limit L, which is the limit of the function as x approaches a. And what we want to show is how this definition of this implies that this is going to be true. And it's important that we have this bit here, and I'm just going to talk about that again. So if we didn't have that condition, then we could have a sequence A, and of course then its image sequence, that sequence would converge to A, so it would satisfy this, but its image sequence would be, for instance, this point down here, so you just have that term f of a, f of a, f of a over again, and of course that sequence converges to f of a, it doesn't converge to the limit L, so it is important that we exclude our actual centerpiece, our point A, from this. So to prove this, we need to start with such a sequence that converges to A, and we need to then prove that its image sequence, which we can construct, so we can take each one of these terms and look at what it's mapped onto by the function. We'll assume that the function is defined for all of these terms. So we can construct its image sequence, and then we need to prove that that converges to the limit L. So I've put a question mark here, so this is what we need to prove. And we need to do that using the fact that this epsilon-delta definition is true over here. So to prove this then, we need to prove that the terms of that image sequence get and stay indefinitely close to the limit L. Formally, we need to prove that for all epsilon greater than 0, for all closenesses, there must exist a big N, a term in this sequence, such that for all the terms that are equal to that term or beyond that term, that the distance between the term of the sequence and the limit is less than that epsilon. So finding this big N is actually beautifully simple, because you can start with your epsilon and then use this here. So we can imagine putting this epsilon interval around our limit L, and then by the epsilon-delta definition, we know that there is going to then exist a delta interval around A, such that all the points inside that delta interval, apart from A itself, are mapped into the epsilon interval around L. And now, because we know this sequence converges to A, we can apply its definition of convergence, which says that for any epsilon, there will exist a big N, such that for that big N and beyond that big N, all of the terms are within that epsilon of the limit, which in this case is A. So we can just use that delta as our epsilon, so there will exist a big N in this sequence, an big nth term, such that that term and all the terms beyond it are then inside that delta interval around A. You can then use that big N as the big N you need here, because if we then look at its corresponding term in the image sequence, f of x big N, that must be inside that epsilon interval, because xn was inside the delta interval around A, and then by the epsilon-delta definition, that was the delta interval that is mapped entirely into this epsilon interval around L. So that means that that term, and indeed all the terms beyond it, because they correspond to the terms beyond x big N over here, are all going to be inside that epsilon interval around L. And you can do that for whichever epsilon you like. So that then proves that if the epsilon-delta definition is true, and you have this sequence that converges to A, then its image sequence must indeed converge to L, providing, of course, we have this assumption that none of the terms of the sequence are actually equal to A, because, of course, that would have broken the epsilon-delta definition, because A itself is not included in this definition being mapped into that epsilon interval around L. So what we've seen now is that if the limit of the function as x approaches A is equal to L by the epsilon-delta definition, then it implies, this arrow that I've drawn here, that if you have a sequence in the domain that converges to A where the terms of the sequence are not allowed to actually equal A itself, then its corresponding image sequence will converge to your limit of the function L. What I now want to show is that actually there's another direction to this arrow. If it is the case that all such sequences in the domain that converge to A, where the terms of the sequence are not allowed to equal to A, then their corresponding image sequences converge to L. If that's the case, that all of those corresponding image sequences converge to a number L, then this arrow goes the other way round. You can conclude that the limit of the function as x approaches A is equal to L by the epsilon-delta definition. We can add another head to this arrow to make it a biconditional, and that's why this is called the sequence characterization of the limit of a function, because it is actually a mathematically equivalent formulation of this concept of the limit of a function. So to prove this then, we're going to start off with the sequence characterization assumption, i.e. that if you have any sequence that converges to A where the terms of the sequence are not equal to A, so any one of these green sequences in the domain, then its corresponding image sequence in the codomain converges to the limit L, and we want to then prove that we can derive this epsilon-delta definition and therefore say that the limit of the function as x approaches A is equal to L. And the way we're going to do this is by proof by contradiction, i.e. we will assume that this is not true and show that it contradicts our initial assumption that this is true. So if this is not going to be true, then we need to negate this. So let's look at this. For all epsilon greater than 0, this complicated thing was true. So the negation of that is that there must exist some epsilon, at least one epsilon, for which this is not true. So that's the first bit that I've written here. There must exist some epsilon, and I'm going to call that epsilon epsilon bar, that is greater than 0, such that this is not true, i.e. the opposite of this is true. Now, there might be multiple epsilons for which this isn't true. However, for our purposes, we only need one. So we're going to take that one of them, and we're going to call it epsilon bar. So let's now negate the rest of this. So the rest of this was saying that there must exist a delta interval around the point A, such that all the points apart from A are mapped into that epsilon interval around L. So the negation of that not being true, means that whatever delta interval you take around A, there must exist a point in it that is not mapped into the epsilon interval around L. So writing that down, it must be the case that for all delta greater than 0, there must exist a point inside the delta interval around A, excluding A itself, such that that point is not mapped into the epsilon interval around L. I'm going to say that again because this is complicated. So this was saying that whatever epsilon interval you take around L, there must exist a delta interval around A such that all the points inside that delta interval, except the centerpiece itself A, are mapped into the epsilon interval around L. If that is not going to be true, then the opposite of that being true is that there exists some epsilon interval, which we're calling the epsilon bar interval, such that whatever delta you choose, however small you make it, all of them, if you construct these delta intervals around A, every single one of them has at least one point inside it that is mapped outside of the epsilon interval that is not A itself. So there must exist an x inside that delta interval that isn't A itself, such that when you look at what it's being mapped onto, it's outside of, it is not an element of the epsilon bar interval around L. So drawing that on the picture here, I have now made this blue interval around L, I've made that our epsilon bar interval, so that's L minus epsilon bar to L plus epsilon bar, and then I've tried to highlight the red interval, once again that's our delta interval, and whatever delta interval you make, however small you make this delta interval, there must exist some point, which I've put in white here, that is not A itself, so some point except A inside that delta interval, that's that white point there, that's that x here, such that when you look at what x is being mapped onto, it's being mapped outside of the epsilon bar interval of L. Now, of course, it doesn't work in this picture here. The picture's showing how it's complete nonsense, because, of course, that white point is being mapped actually onto something inside the epsilon interval. But if it were true that this is not true, this must be the case. And the reason, of course, it doesn't work on the picture is because the picture is showing an example where this is true. So that's why assuming that this is not true isn't consistent with the picture. However, the picture wasn't our starting assumption. This was our starting assumption. So we need to use this to find a contradiction in this rather than a contradiction in the picture. So to contradict this, we need to be able to use this to construct a sequence in the domain that converges to A, where the terms of the sequence are not going to be A's themselves, where if you look at its corresponding image sequence, it doesn't converge to this limit L. So this is how we're going to construct such a sequence. We're going to start off by considering a delta interval of size 1. So delta is equal to 1, and you can think of that red interval there as being this delta equals 1 interval around A. Now, because this is true, it must be the case that there exists some x inside there that is not A, that is mapped outside of the epsilon bar interval around L. Those are those white points in this picture up here. Take whatever that x is in the domain and call that x1 and make that the first term of your sequence. And then if you think about what the image corresponding term in the image sequence is, f of x1, we know now that that is going to be mapped on, it's going to be something that is outside of that epsilon bar interval around L. Now to get the second term of the sequence, half the size of the interval, consider delta is equal to a half. Again, on this picture, we can now use our red interval to represent the delta is equal to a half interval. And again, because this is true, there must exist some point inside that interval that is not A itself, that is mapped outside of the epsilon bar interval around L. Take that point and put that as your second term of this sequence. And again, if you look at its corresponding term in the image sequence, we know that that is going to be outside of the epsilon bar interval around L. Now, it does not matter if these two terms were the same number. Of course, this interval contains this interval, so it might have been the case that you chose the same number from both of these intervals. That doesn't matter, so they can be the same. To get the third term of the sequence, you then progress again. Half the size of the delta again will go to a quarter, and then by the same logic, there must exist a point inside that quarter interval that is not A itself, so all the terms of the sequence are not going to equal A, such that if you look at what it's mapped onto, it will be outside of that epsilon bar interval, so its corresponding term in the image sequence will be outside of that epsilon bar interval. Make that point your third term, and again, it might be the case that all three of these were the same number, because this interval contained this interval, and this interval contained this interval, so it might be the case that all of them were the same number. That doesn't matter, because at some point you're going to progress onwards. We're going to continue halving the size of these intervals, and at some point this sequence will have to progress on, because you'll get to a size interval that doesn't contain these previous points. So to generate the sequence then, you continue on in this manner. You keep halving the size of the delta interval. So to get the nth term, you will have a delta equal to 1 over 2 to the power of n minus 1. It's not quite 1 over 2 to the power of n. You have to have that minus 1 there. If you look at the way we've done this, this second term was 1 over 2, so it was 1 over 2 to the power of 2 minus 1. This third term was 1 over 4, not 1 over 8. So it is necessary to have that n minus 1 there. So you create this delta of this size, you look at that interval, and again, there must exist a white point inside there such that it's not equal to A, and it's mapped onto something strictly outside of the epsilon bar interval around L. Take that as your nth term, and then you know that its corresponding term in the image sequence is going to be strictly outside of that epsilon bar interval around L. Now this is a problem because this sequence that I've constructed in the domain is clearly going to converge to A because of the way these delta intervals are halving each time. That means that the terms of the sequence are going to get indefinitely close to A, and also they're going to stay indefinitely close to A because actually all the subsequent terms are inside each of the previous delta intervals as well. They're in even smaller delta intervals. So clearly this is going to converge to A. The problem is then if you look at this image sequence that I've constructed, I constructed the terms of this sequence purposefully so that the image sequence is all going to be outside of this epsilon bar interval around L. So that means that this sequence can't possibly converge to L because it can't get indefinitely close to L. It can't get within that epsilon bar of L. So I have therefore found a contradiction to this. If you assume this is not true, it contradicts that every one of these sequences in the domain that converges to A, where the terms of the sequence are not equal to A, must have or has a corresponding image sequence that converges to L. Here I found one that doesn't, if that's not true, and therefore it can't be true that that's not true. This must have been true. So we can now add that other arrowhead onto here. The sequence characterization of the limit of a function and the epsilon-delta definition of the limit of a function are mathematically equivalent to one another. So if for all sequences in the domain that converge to A where the terms of the sequence are not allowed to equal A itself, their image sequences converge to the same thing, some value L, then you can conclude that the limit of the function as x approaches A is that value L that the image sequences are all converging to. Before we move on, I would like to point out that this sequence characterization, which at the moment is extremely broad, can be made more restricted. And this restriction that I'm going to show you is going to be extremely helpful later on for certain results that we want to prove. So at the moment, these sequences aren't really restricted at all. They need to converge to A, and they're not allowed to have any terms equal to A, but apart from that, these terms can be whatever you like. The tail end of the sequence, yes, has to converge to A, but the finite number of terms at the beginning of the sequence could be all over the real line. Now that's going to be annoying later on. At the moment it's not causing any problems, but it is going to be annoying later on. So what I want to show you is that actually this equivalence holds true even if we restrict these sequences further, and this is how we're going to restrict them. You are going to take some radius, which we will call r, so it's some number, some real number that's greater than 0, and you're going to look just at this interval around A, so the interval a minus r to a plus r, and you're going to just let the terms of the sequence be inside that interval. And if you put this restriction on these sequences, so they're still going to converge to A and they're still not allowed to have terms equal to A, then actually this equivalence is still going to hold true. And actually you can make this r as small as you like, as long as it's some positive real number. You can take terms in the sequences just from an interval however small you like, and if all of their image sequences converge to L, that's going to be equivalent to this epsilon-delta definition for the limit of the function equaling L as x approaches A. So that's going to be extremely helpful because now we have much more control over what the terms of the sequences are going to be in this sequence characterization. So let's just understand why we can weaken it like this and this equivalence is still going to hold true. So proving it in this direction, this arrow, is very simple. We showed that if the epsilon-delta definition is true, then actually any sequence that converges to A, its image sequence will converge to L. So now these sequences that are restricted to terms being inside this interval, they are all still going to apply. You know, that initial proof is all still going to apply. So their image sequences are still going to converge to the limit L. So that direction is very simple. Let's now prove the other way round for our restricted sequences. So we're going to start this time with the assumption that all sequences that converge to A, where the terms are not allowed to equal A, and they're within this restricted interval where R is some positive number, their image sequences converge to L, and we want to show that this is true. And we're going to proceed with the same proof by contradiction that we had before. So if this is not true, then this again must be true, that there exists some epsilon bar greater than 0 such that all the delta intervals that you consider have an element inside of them that is not A itself, that is mapped outside of the epsilon bar interval around L. Now we need to show, as we did before, that if this is true, we are able to construct a sequence that converges to A where the image sequence is not going to converge to L, contradicting our initial assumption, but this time our sequence is going to need to be in this restricted interval. Now we're able to do that simply by changing the deltas that we use. Instead of starting with a delta equal to 1 and then halving it, we'll start with delta is equal to r, because r might be smaller than 1 now. So we'll start with delta is equal to r, then we'll go to r over 2, then we'll go to r over 4, and so on, and halving each time. So for delta is equal to r, there must exist some number inside it that is mapped strictly outside of the epsilon bar interval. Pick that number, make that your first term. For delta is equal to r over 2, again there will exist something that is not A, that is inside that interval, that is mapped outside of the epsilon bar interval. Make that your x2, and continue on like so. Hopefully, again, it is clear to you that this sequence will converge to A because of the way we are selecting them inside these progressively smaller and smaller intervals that are centered around A. The terms of this sequence are also all inside this restricted interval now because the smallest interval was of radius r, and then all the other intervals are smaller and therefore are nested inside of this. So they are all terms inside our restricted interval of consideration. Also, none of the terms are going to equal A because of the way we are selecting them. We are selecting them as the thing that's inside the delta interval that is not A, that is mapped outside of the epsilon bar interval, which, if this is true, must exist. However, so we have a sequence, therefore, that converges to A that satisfies all of these criteria, but of course the image sequence cannot possibly converge to L because all of these images are being mapped strictly outside of the epsilon bar interval and therefore cannot get indefinitely close to L. So it would contradict this. So yes, we have shown that if this is true, it also implies that this is true. So that's going to be very important later on for certain results that we want to prove, that you can weaken this sequence characterization criterion so that the terms of the sequence are only allowed to be in a restricted interval around A, and you can actually make that R as small as you like. I didn't specify what it is. This argument that we've just used applies for all of them. So we can actually consider an interval very, very small around A and just use terms in our domain sequences from that small restricted interval. So this is like in sequences where the front part of the sequence can be cut away and you can just look at the tail end of the sequence. It's the tail end of the sequence that determines what the limit is. The front part of the sequence might be doing something crazy. It might be dotted all over the real line. It doesn't matter. You can just cut it away. That's kind of what we're doing here. We're cutting away and then we're just looking at the tail end of the domain that is tailing in to our point A. And just like in sequences where you can cut as much of the front off as you like, you can go as far along and cut it away as you like, we can cut this up as far as we like as well. We can make this R as small as we like and then cut just that tail end of the domain that is tailing into A. And it's just that tail end, what the function is doing for that tail end of the domain that's tailing into A, that determines what the limit of the function is going to be, not what these other parts are doing that are finite distances away from A.